Mm, 200 have joined. Mm, we can just wait for a couple of minutes. Yeah,
Yes, sir.
right. Okay, then I think we can start. Uh, about 200 plus. Okay, others will join, I hope. Okay, okay, guys. As we planned yesterday, we'll continue from Shor's algorithm. Sorry, we continue from Dutch algorithm and Dutch Joyce algorithm, and the next algorithm is Bernstein's Vajrani algorithm. Okay, right? So, what is this algorithm is all about? Okay, I already told you it's an extension of Dutch algorithm. So let's see the few uh, insights about Bernstein's Vajrani algorithm, which I have listed here. Okay, so we will just see that. Okay, fine. So it is developed in 1992, right? And introduced in 1997. Okay, somewhere very close to the time Shor's algorithm and Grover's algorithms were introduced. At that time, this also being introduced. Okay, so 97. In fact, it could be seen as an extension of Dutch Joyce algorithm. As you recollect, Dutch algorithm is calculating multiple function values in one shot, and Dutch Joyce algorithm is calculating the sum of function values and finding the function is being uh, even sorry, balanced or a constant function. Okay, so that is what we saw yesterday and day before yesterday. Now it showed that there can be advantages in using this in a quantum computer as a computational tool for more complex problems than Dutch Joyce algorithm. In fact, this is starting point for real world applications. Somebody was asking earlier, what is a Dutch- sorry, what is a Dutch algorithm and Dutch Joyce algorithms, the real world applications? Okay, so you can think that this would be a starting point for the Dutch algorithm. Okay, so I have given a reference for you. If somebody wants to know, they can check that the details. Okay, let's go further. Applications of Bernstein's Vajrani algorithm, BV algorithm, in short. Okay, it is known to solve a hidden shift problem. Okay, which has important applications in cryptography and error correcting codes. Very important. Okay, what is hidden shift problem? Okay, that we will see throughout this today's session. Okay, right? And there is some details here for a given function. Okay, x string, function with x string, there would be a hidden shift. Yes. Okay. Right. A string is shifted by some means from one form to other form using some shift s. Okay. The goal is we need to find that shift. Okay. It's like a number changes are increased or decreased by some amount. For example, here in this case, yes is that amount. Now the question is, somebody did it and we want to find what is that shift. Now the game would be, our task would be like, I want to find the shift by seeking less number of queries from the person who did that shift. That is the task, like a game which we played or which we understood yesterday in Dutch Joyce algorithm. Between Alice and Bob, Bob uses a function f of x, which could be balanced or a constant. Okay. And Alice has to find out what kind of a function Bob is using by seeking very less number of, okay, very less number of queries. Okay. That less number of queries, usually with the classical algorithm, would be some number. Okay. But if I use a quantum algorithm with a quantum mechanical principles like superposition, entanglement, and these things we bring in, you can reduce the number of queries to just a single query. That is what we saw yesterday. Now here also we need to find the shift s by asking very less number of queries. Okay, so that is what we want to know. Now, yeah, now just to see the working principle here, I have a working principle for you, and working principle is actually rely on few things. Number one is it relies on phase kickback. Okay, right, and it relies on finding a function f of x, what could a function, and that function is just like we saw yesterday, constant balance. That function is this shift multiplied by bit shift multiplied by the x argument value or x argument string. Okay, so this function value may go to 0 or 1 with addition modulo, constraint. Okay, right. So here if you remember, x is an argument, s is a shift. Okay, bit by bit s and x gets multiplied and adds up. Okay, and gives us what is the f of x value. Okay, what I mean, okay, the shift function f of x is s dot x modulo 2 modulo 2. What I mean is, let's say you substitute some x value, say x1, x2, x3 and so on, xn. It's a string for it. Okay, if you substitute, and s dot x would be, the shift function would also have a string of inputs or the numbers, which would be s1 x1, s2 x2, s3 x3 and so on, sn xn. Whatever is this value, let's say the overall value is, let's say, some r, which is converted into addition modulo 2. Some value will get, that would be either 0 or 1. Okay, so it would be either 0 or 1. Based on that, we can find whether the function is f of x is using what kind of a shift. Usually I have to ask what is the s1, what is the s2, what is the s3, and so on up to sn. I have to ask the entire string length of s. Okay, the n number of attempts or queries are required. Okay, right? So that is what the function is mean here. Now, before that, there is something else, that is phase kickback. What is this phase kickback is? It's a technique to determine n bit hidden shift or hidden string on a quantum computer using a block box function. Okay, what is a block box function? Just see on the right. Okay, so let's understand what is a phase kickback. Right, okay, let's shift to things which we wanted to understand, to go to okay to go to this persistence Vajrani algorithm. So first thing I want to understand is phase kickback. Okay, for example, consider C naught gate. Okay, if you consider a C naught gate, what happens? C naught gate is having two qubits, one control, another one is target. Okay, let's say there is a qubit 0, qubit 1. Depending on qubit 0, target gets manipulated, changes. Okay, its flips or not is decided by the control. So what I mean is the information here is traveling from top to bottom. The flavor or the effect of control is traveling from top to bottom. So that is what usual way we see, right? Why we say is control always remains the same. Target gets modified. For example, target modified by Q0 value. Okay, so this is what happens in CNAT kit. But if at all, if there is any other way, if we could make information to travel in a opposite direction, in a opposite means bottom to top, okay, in a opposite direction. Okay, if it is possible, then that could be a information kickback, means going back whichever direction is supposed to come. Okay, it's called a phase kickback. Okay, so what in here, instead of information, I would say a phase is being kicked back. Okay, so what I will do now, for that we could use a Hadamard gates, Hadamard gates here. How do we use is very interesting. You take Hadamard, okay, right, another Hadamard, one Hadamard, another Hadamard. So, and in between you take control NOT gate. Okay. Now, usual way you see things is you think that information always comes down from the top to bottom because of the C naught gate. Because of the adamants on the either side, what happens in fact, it becomes a equivalent to the reverse. Okay, right? So information travels upwards instead of coming downwards. What you can do, you can cross check actually. Suppose if I have, let's say, 1 0 1 kit 0 kit. Okay, so I'm trying to understand here. If I don't have any hadamats, what I'll see, the output is just 1 1. But here I have hadamats. Okay, let me see what is the psi naught, what is the psi 1, what is the psi 2, what is the psi 3. Okay, so there are three. Okay, 1 minute. Yeah, I'm sorry. So I want to find various level what is the quantum states. So first thing is psi naught. What is the psi naught? Okay, 1 tensor 0. What is the psi 2? Sorry, psi 1. Hadamard acting on 1, another Hadamard acting on 0, which is 0 plus 1 get divided by square root of 2 tensor 0 minus 1 divided by square root of 2. Okay, now let's take what is the overall setup would look like, which would be 0 0 plus minus 0 1 plus 1 0 minus 1 1 divided by 2. Now this is the psi 1. I want to find psi 2. Psi 2 is C naught acting on psi 1. Psi 1 is this one. So let's see now, when control is 0, target remains. When control is 0, again target remains. When control is 1, target flips. When control is 1, target flips. Okay, I just got what is the psi 2. Okay, let me rearrange the psi 2 for our own comfortability. If there is any commonality you can take, let's say I take a, from first two terms I can take 0 get common, 0 minus 1. Okay, right? From second terms I take 1 get common, 1 minus 0 get. Okay, divided by square root of 2, so just 2, which I will write now 0 get plus 1. Okay, 0 cat minus 1 cat. What I will do, I will just instead of just taking uh, is from the second term, I will also take minus 1 common. So if I take a minus 1 common, what happens? This becomes minus 0 plus, okay, 1. I'm sorry. Okay, wait a minute. It's a minus, minus, minus. Okay. Earlier, 1 was there for minus 1. Okay. Right. Let me go back and show you what exact. This is what I have. Now, I want to take a common of 0 minus 1 get common. Okay. So let me take that as a common. That would be easier to see. 0 cat minus 1 cat common. If I take the first element is 0 cat, second element is minus 1 cat divided by, there is a 2, I'll have square root of 2 here, square root of 2 here. Okay, right? So now psi 2 is, okay, 0 cat minus 1 cat divided by square root of 2, 0 minus 1 cat divided by square root of 2. This is what I have. Now I want to find what is the psi 3. Psi 3 is Hadamard acting on the control tensor, Hadamard also acting on the target. So that is a psi 2, which is going to give me what? Hadamard acts on this, Hadamard acts on this. What do I get? 1 cat and 1 cat. You see, 1 cat I got. So what did I start with? I started with, okay, I started with 1 0 and I left with, okay, 1 1 1. So that's fine. Okay. Now it, in a way, it acts like the information actually traveled forward. You know why? You see, this is what I had after the C not gate. Okay. So what is this? This is supposed to be, okay, this one plus and minus, sorry, plus 0 cat plus 1 cat, but it has become 0 minus 1 cat, as if the information is traveled from target to control, and due to that it has changed. Okay, right? So what I was having earlier 1 0, right? Now it has become, okay, just a minute. Yeah, it was having 1. So before having Hadamarts, this second two Hadamarts, what I see is the control part got modified. So usually it doesn't get modified in the case of control not gate. So this is a phase kickback for you. Phase kickback. Okay. I have one more example in the PPT that we will see in the PPT. Okay. Fine. So I was just showing the control knot from top to bottom becomes bottom to up when I have Hadamarts. Okay, that's important. Now, the shift function, the fifth shift function is some kind of the reverse controlled unitary gate. Okay, so usually we think that information travels from top to bottom. Okay, but we can make it to go upwards, bottom to up, from ancilla qubit to upward by using the Hadamard gates on the either side. Okay, right? So that is the main principle of Weierstrass-Vajrani algorithm. Okay, so there is an intuition behind using this technique. What it does, it exploits the superposition and entanglement properties of a quantum mechanics to effectively determine the unknown strings. What is that unknown string? S is an unknown string which we want to find. So here the algorithm uses a quantum oracle that applies a function f of x to a given superposition for all possible inputs in parallel. in parallel, remember. Okay, the resulting quantum state carries the information of S. Okay, and by measuring the quantum state, the algorithm can extract the bits of S one by one with a high probability. Okay, right? So let me give a simple continuation analogy from Dutch algorithm to Bernstein's-Vajrani algorithm. If you recollect Dutch algorithm, I have unitary function x, I have y input, x goes as it is, y gets add up the function of f of x. Okay, this is with the Hadamard. Okay, how many Hadamards? Depends. Okay, there is a zeros, n zeros. Okay, and there is a fine. There is a ancilla. This is what we have a Dutch algorithm. For Dutch Joysa, sorry, yeah, for Dutch Joysa, I will also add one more Hadamard here. Okay, so this, yeah, this later part I'll have. So this is a Dutch Joyce algorithm. Now, Bernstein's-Vajrani algorithm is very close to this. Okay, only difference here is I'll have n qubits, I'll have n Hadamards. I have one ancilla, one Hadamard for that. I have one oracle function, which is a unitary function for sure, right? So unitary function, what kind of a f of x? F of x is s dot mod 2 is taking 0 or 1. That is a function. Now here I have x, here I have y, here I have x. Okay, right? But my y is very, very interesting. My y gets modified not by adding f of x, it is modified by adding s dot x. So that is a function is going to be modified here. Okay, so how it is done, we will just see by step how in a circuit. Okay, right? So this is a modification. Okay, so let's see in my PPT what I have. It exploits, okay, this point we have just saw. Algorithm uses a quantum oracle that applies the function f of x to the superposition of all the possible inputs in the problem. So the superpositions are coming from here, okay, and here, and it applies that f of x to that. The resulting quantum state carries the information of yes. So at this point, I'll have an output where the information of S is carried. Okay, by just querying, understanding the query part, by let's say I have output, by studying the query part in the output, we could extract the S information. Okay, very, very important. Fine. So the algorithm can extract the bit S one by one with a very high probability. Okay, means success rate is very good. Okay, so one simple okay, let's say I don't have a classical exam. If I don't have a quantum computer, if I want to do classically, okay, right? So there is a shift function. Let's say there is let's say I have a string x. Okay, sorry, not a string x. Let me take some other number. Let's say I have some other number. Let's say some y is equal to 1001. Let's say I have that, which is shifted by some value. What is that shift? Shift is yes. What is the shift? Shift is 1101. So this is a shift string. This is the string what I have. The string what we have. This is the shift string. Let's say now I want to find what is this shift string. How what are the bits in it? What I have to do, I have to ask bit by bit to somebody who is doing the shift. Let's say I should ask, is your first bit string, first bit is 0 or 1? Okay, the person who is using, he will tell me it is 0, 1 query. Second one, similarly, he has to give me, with the 4 queries, I'll find all the 4. Okay, right? Classically, that is what done. So what I will do, right? I will ask, is your first one is 0 or 1? How do I do? I will just take my x is 1, all zeros, and multiply to the s, and I'll get an output. Okay, right? So what is this? This is a bit by bit multiplication and addition. If you carefully see, what is the output? 1 into 1 plus 0 into 1 plus 0 into 0 plus 0 into 1. What is the output? Just 1. So that is the one I'll get. Similarly here, first query is that. Second query is, I will ask whether the second bit string is 1 or not. How do I do? I will multiply it to the, okay. How do I ask is, I'll give my x to the person, ask him to calculate f of x and give to me what is the value. So what he does, he multiplies whatever I have supplied. I supplied x is equal to 0, 1, 0, 0. He multiplies 0 into 1 plus 1 into 1 plus 0 into 0 plus 0 into 1. What is this? Again it is 1. So he will just give me what is the f of x. So f of x is 1, 1. And the third case also, he gives you a 0. Okay. So from there, I would find out what is the f of x format. What is this? Sorry, from there I'll find out what is the s would look like. So the values of functional values itself will tell me what is the s. So this is a classical algorithm. At the most, definitely it requires 4 queries. Okay, so 4 queries. Now what quantum algorithm says is, if I use this quantum circuit with a phase kickback, okay, it uses two important properties. One is superposition and phase kickback, and it uses superposition and Hadamard gates to generate multiple states that can query the oracle, okay, like we did. So this is a part of query, okay, in our, so this is a query, okay, and an ancilla qubit is added to the circuit so that the interaction between query and ancilla bits leads to solution. So this is an ancilla. So this is it's a plus, oh, sorry, minus ket. Okay, so this is where I have minus ket, and this is where I have superposition of many possible qubits. Okay, for example, here in this case is a superposition of x belongs to 0 comma 1 tensor n x cat divided by 2 to the power of n. That is the query part at this point. Okay, right? So that is what it says. This is all queries, and this is the ancilla. Okay, and a phase kickback is used in such a way that the control is at the top of the qubit. The phase change also affects the top qubit. So usually we think information travels from control to target, but it does the other way around. What is that? The information travels upward with the phase information is added from bottom to the top to this f of x processing. From there, we will get to know, and here some output we will get. So that output we will query or analyze, and from there we make out what is the S would look like. So that is why it's given as S get. Okay, analyze and get S. Okay, now like I was telling you earlier, one example for a case phase kickback I want you to see. So what is this phase kickback is? Let's say I have, okay, I have a zero kit. I have a zero kit at the bottom. I use a Hadamard gate. So Hadamard gate puts these things into superposition. 0 plus 1 by square root of 2. So that is what here. And after the Hadamard, in the bottom, I'll have a X gate for the query part. So this is where I'll have one kit. So what is the overall state? 0, 1, 1, 1. Okay. Now that goes through a controlled phase gate. Right? What is a controlled phase gate? Controlled phase gate is just like a Z gate. Okay. Z gate is exponential I pi. Right? And this is a Z gate. Okay. What is a Z gate? That it adds a phase angle of pi. If I want to have a phase angle of pi by 4, I use a phase gate of pi by 4, which is 1 0 0 exponential I pi by 4. Okay, right? So what it does, it only adds a phase to 1 ket. It doesn't add phase to 0 ket. That is what you see here. And remember, the phase gate is a controlled phase gate. Means whenever control is 0, that time there is no phase adds. Whenever control is not 0, 1, it happens. Okay. So, okay, let me elaborate. Z is 1 0 minus 1, which is 1 0 0 exponential I pi. You know why? Exponential I pi is cos pi plus I sin pi. Okay, right. Cos pi I sin pi. So which is going to be a minus 1. So second term is 0 anyway. Fine. So Z is a phase gate of pi angle. Now I want a phase gate of pi by 4 simply, which is 1 0 0 exponential I pi by 4. Okay. Now I just don't want just a pi gate, phase gate. I want to have a controlled phase gate, which would be just similar to control not. Okay, right? In place of not, I'll have a phase. Okay, this is a controlled phase gate. Okay, fine. So now we are understanding what is the Hadamard ix gate, and then a phase gate. Okay, this is we are trying to understand. This is a 0, this is 1. At this point I have a equal superposition. Here I have 1 gate. Now if I think that this is a psi naught and this is a psi 1 and this is psi 2. Okay, psi naught is 0 1, psi 1 is 0 plus 1 divided by square root of 2 multiplied by 1 kg. And psi 2 is controlled phase acting on psi 1. Okay, to understand that, we were trying to do psi 2 is Cp pi by 4 acting on 0 1 plus 1 1 divided by square root of 2. Now as you can see, whenever control is 0, the target will not see anything. But whenever is a control, target is being added with exponential I pi by 4. So that is what exponential I pi by 4 1 1 ket divided by square root of 2. Now you see, I can take the common. I can take the common of 1 ket. What I'll have? 0 plus exponential I pi by 4 1 ket 1 ket divided by square root of 2. Now you see, the target remaining same intact, but the control is being added with the relative phase between their 0 ket and 1 ket, so that we don't usually anticipate. We anticipate there is something happen to the control from left to right, but instead of control being getting manipulated, target is being manipulated. So that is what the phase kickback. The phase of exponential I pi by 4 is travel from bottom to the top, from target to the control. Okay, so that is what I meant here in this case. Okay, so very important. Fine. So only the phase affects the first qubit, even though it is a control. Now versus Vajrani algorithm, we can understand using few more shorthand notations. What are those shorthand notations are? Okay, let's use my hand notes to understand few uh, derivations. I would say few derivations. Okay, right. So yesterday we tried few derivations for Hadamard action. So that is what we will do it for today also. As you know, Hadamard acting on 0 gives you what? 0 plus 1 kit divided by square root of 2. Okay, and Hadamard acting on 1 gives you 0 minus 1 square root of 2. I just want to bring some kind of a, okay, our target is to have a f of x is s multiplying to x mod 2. Okay, that kind of a function I want to have. The effect of s dot x acting on the some argument which is coming into the function. Okay, so that the s value we can retrieve. So in that fashion, let's say Hadamard gates are involved in my function. In that case, how can I explain? Just like s dot x kind of a thing. So for that, what I will do, I'll use a trick. What is that trick is, Hadamard acting on 0 is equal to, I'll write it as 1 by square root of 2 minus 1 to the power of 0 into 0. Okay, take 0 ket plus minus 1 to the power of 0 into 1 1 ket. So here This second 0 is coming from here. Second one is coming from here. And what is the first 0? First 0 is this. Okay. So this will make sense. You know why it makes a sense? Because if I use this kind of a notation, okay, the left hand side is satisfied. Similarly, for h acting on 1, I will do the same kind of analogy. I will say minus 1 to the power of 1 into 0, 0 ket, plus minus 1 into 1 ket. Sorry, 1 into 1, 1 ket. Same here, the right 0 comes from the kets, the left 0 comes from here. Okay, right? Okay, so let me remove this slightly. Okay, now it makes sense now. Now what I will generalize H can act on any kind of A. Okay, right? It can be it can be 0 or 1, means I'll have an output minus 1 to the power of A into x 0, 0 ket, plus minus 1 into A into 1, 1 ket. Okay, right? So I am a little lazy. I don't want to write two terms. I'll write it as a one term on the right. What is that? Is 1 by square root of 2 summation over x belongs to 0 comma 1. Okay, minus 1 to the power of a into x, x ket. Okay, you see now, if you recollect back, it is something very close to unitary acting on x 0 ket minus 1 ket divided by square root of 2, where what was the output? Output is minus 1 to the power of f of x, x ket 0 minus 1 divided by square root of 2. So please recollect this equation derived earlier as a part of Dutch algorithm. Okay, but now for a Bernstein-Swajrani algorithm, we are actually using Hadamard action on a given bit string as, okay, something like this. Okay, which is going to be very useful for us as we go through, right? So fine. So for a single qubit, this makes sense. Okay, for let's say a 2 qubit system, right? This is a single qubit case. Okay, but if I have a 2 qubit case or any n qubit case, what it will be? Okay, right? For a 2 qubit case, what I'll have two Hadamards acting. There is a Hadamard square acting on 2 qubits. Both can start in 0. So what it will be? It will be H acting on 0, 0, as you know, which is H acting on 1, 0, H acting on another 0, which is 0 plus 1 divided by square root of 2, 0 plus 1 divided by square root of 2, which is in fact 0, 0, 0, 1, 1, 0, 1, 1 divided by just 2. Okay. Similarly, you can also derive for the case of H acting on 0, 1. For a 0, 1, you can find out which is 0, 0 minus 0, 1 plus 1, 0 minus 1, 1 divided by 2. Similarly, you can find for H square acting on 1, 0. slightly different. 1 by, sorry, okay, right, 1 by 2. I'll take the output, it's easy. 0 0 plus 0 1 minus 1 0 minus 1 1. You can cross check if you want. And for what about 1 1 case? It would be 1 by 2, 0 0 minus 1 0 1 minus 1 0 plus 1 1. Okay. So this is what happens when two automates acting on two qubits, the starting with 0. With a 1 qubit, 1 Hadamard, we got a formula. Can we do it for 2 qubit case, or can we do it for generalized case? Of course, yes, it's very, very easy. What is that is, we will just say generalization to n qubits. Okay, what is that is, we simply say h Hadamards, n Hadamards acting on a string of A's. Remember, A is having A1, A2, A3, AN. Okay. In that case, what is the output? Output is 1 by square root of 2 to the power of n summation over x belongs to 0 comma 1 tensor n, okay, minus 1 to the power of a into x bitwise multiplied by x kit. Okay, so this is just the extended version from 1 qubit to n qubits. So only difference from earlier case to here, if you see, earlier case I have just 1 qubit and now I have n qubits. Okay, so the probability amplitude gets modified according to that, and the summation also gets modified according to that. So this is also plays a very, very vital role in our calculations. Okay, so now the Bernstein's Vajrani algorithm, okay, is consisting of, okay, a function f of x dealing with Hadamard gates. That is what it has. Okay, so the first thing in the Bernstein's Vajrani algorithm, the BV circuit. Okay, what it's consisting of is, first it's consisting of several query zeros. Zeros. How many? Depending on the strength. So all of them are 0, 0 and n zeros. Okay, and there is a Hadamard acting on each one of them. Okay, Hadamard acting on each one of them. So this is written as Z0 tensor n, and these are written as n Hadamards acting on them. So what is the result here? Okay, the result here is H tensor n acting on 0 tensor n is 1 by 2 to the power of n summation over x belongs to 0 comma n tensor n x. Okay, now right now I have just created a equal superposition. This is here equal superposition states. Equal superpositions. Okay. Now after equal superposition, I'll have a unitary function. Right? So let's say this is all query part. So that comes here, and I have a ancilla part. So there is a x, there is a y. So there is a unitary function. X goes as this, and y gets modified as per the function. Okay. Now it's not just addition f of x. What is this oracle function is? Now let me change that. Let me change this. It's a oracle function now. OF. Okay. What is this is going to do is it is going to replicate in such a way it is going to add minus 1 to the power of a dot x multiplication. It will add to the entire function. Okay, so what is that? Here I'll have, okay, what I'll have is oracle function getting multiplied to the query part. Instead of having effect on the target, it will also act on the query. So query gets multiplied by minus, okay, so this gets here minus a dot x get. Okay, now that is what we will see. But in our case right now, what we have a x is, in our case, is a equal superposition situation we have. Now what is the effect of oracle function acting on the equal superposition? What was the equal superposition? I have 1 by square root of 2 to the power of n summation over x belongs to 0 comma 1 tensor n x kit. On this, what is the effect? On this, what is the effect? Simply you just straight away bring this inside. Okay, so that would be x belongs to 0 comma 1 tensor n minus 1 to the power of, okay, a dot x kit. Okay, right. Now at this point I have another set of Hadamard's acting on the query. Okay, so there are stages. Remember, I have my ancilla 1. So I'm not bothered about what happens to the ancilla, because the effect of the ancilla or the presence of the ancilla is traveled from the bottom to the top. It's like ancilla becoming a control, and whatever is the control earlier, it becomes a target. So ancilla comes as it is. Okay, it comes as it is. Okay, so that's why I'm not worried. Only I'm worried about what is happening to the target, sorry, control. So right, if I note down, so this is very early stage, this is psi naught. Okay, at this point let's say I have psi 1. At this point let's say I have psi 2. At this point I have psi 3. Right now where we are at, we are at the psi 2. What is the psi 2? Psi 2 is 1 by square root of 2n summation x belongs to 0 comma 1 tensor n minus 1 to the power of a dot x cat 0 minus 1 divided by square root of 2. Ancilla part also I wrote down. Now what is the psi 3? Psi 3 is Hadamard's acting on the query and one identity acting on the ancilla. Okay, so now what I have to know, what is the effect of Hadamard's acting on this? Okay, just right now we have arrived that result. So what I'll do, I'll let me write down. This would be equal to, okay, 1 by square root of 2 to the power of n summation x belongs to 0 comma 1 tensor n. Okay, right? So since this one going inside, okay, so there is a summation over n case it is doing. What I will do, when it goes inside, I can just ignore n. Okay, so you can just simply say minus 1 to the power of a dot x H acting on X, 0 ket minus 1 ket divided by square root of 2. Okay, right? When it comes outside, I can have tensor here, but when it inside, I just simply say H, because I'm talking about for us H being acting on, if the X is just a single argument like a 0 ket, so H will be simply H into X, which is H acting on 0. If X is 0 0, in that case H square will act on X ket, which is H square 0 0. So due to that, according to the I have written H. Okay, fine. Now that is what we will have. Now this effect on this would put the information of yes out. Okay, so just to see how it happens, let me show you the circuit. Okay, yeah, we came up to here. Now this is a circuit. Okay, so this is a circuit. Now first I prepared 0 0 and 1. Okay, so this is the size 0, and then I creating equal superpositions of queries. How I am acting Hadamard on 0, another Hadamard on 0, another Hadamard on 1. So this is the ancilla, ancilla, and this is the query. Okay, right? Now the oracle function I was saying, the oracle function, which is a controlled, two controlled NOT gates. Okay, so the two controlled NOT gates will help me to impart the information from the top to bottom. But since I have Hadamarts here, it becomes a reverse. Okay, so it becomes a reverse. Then, and I will have two Hadamarts put back the quantum states from superposition to the normal computational basis, and then I'll make a measurement on the query. This is a query measurement. Okay, right? So just to give a thought to this circuit, okay, we'll take a 5 minutes break, and after we come back with a 5 minutes break, we'll just see how step by step what is happening in the circuit. Okay, right? So you can just stare at this circuit. I'll just magnify. Okay, this is VB circuit, Master's Vajrani circuit, and then just take a break of 5 minutes, and we'll come back. Yeah. Yes. Welcome back, everyone. Yeah. So I was asking you people to just stare at this circuit. Okay. So this is a circuit which, okay, which has a shift function. This is a circuit for a shift function. S is 1, 1. Okay. So how do I know? Based on what kind of a oracle I have been used, oracle function. 1 minute. Yeah. So what kind of a oracle function we are using? The oracle function is using here is two C naught gates. One from Q0 to ancilla, another one Q1 to ancilla. So based on that, the oracle function is defined. Our oracle function itself will bring that shift function. Okay. So remember, the oracle function keeps changing depending on the shift. Okay, that's what we wanted to do, right? In the first place, if somebody shifts the given number by some amount, what is that shift amount I want to find? So to how to find that is using a very less number of queries. So here the queries I am doing is just one processing through the quantum circuit. Okay. Now, if you carefully see now, if I had to list down the layer by layer, what is the quantum states are. So initial quantum state is psi naught, which is 0, 0. That is at this point. I will not write a query part because I'm not worried about that. So I'll only about, sorry, I'll not worry about the target part. So I'll not write anywhere. So after two zeros going through two Hadamard's, it becomes four equal superposition states. That is psi 1. So that is here. Okay. Now comes oracle function, which is having the information of, okay, which is having information of the shift function or shift vector. So in fact, it is a two control NOT gates running between the queries to target. How they will act? If there is something goes into the oracle function, right? Some xget goes through oracle function, it gets modified by minus 1 to the power of x multiplied by 1, 1. So this is the shift function. Okay. So what is a corresponding shift function based circuit? Two C NOT gates. Remember that. So the shift function keeps changing. If I have a shift function something else, I'll have a different oracle. We will see several examples. I will show you using some simulator. You will understand with that. Okay. Now the x means x in our case is a psi 1. Psi 1 goes through the oracle function, becomes a psi 2. Okay, I have written here psi 2. So psi 2 here is, the psi 2 here is minus 1 to the power of 0, 0 x multiplied by, and shift functions 1, 1. Next, minus 1 to the power of 0, 1 multiplied by shift function 1, 1. 1, 0 shift function 1, 1 shift function. In that way, if you calculate, remember it's a bit by bit multiplication. So here the bit by bit multiplication is 1 into 1 plus 1 into 1. That is 1 plus 1 is 2, modulo 2 is equal to mod 2, mod 2 is equal to 0. So this is like minus 1 to the power of 0, so which is a plus 1, so I'll have plus 1. Accordingly, we will have, whether I have a minus sign or a plus sign, we will get. Now you see psi 2. Now on the psi 2, I'll have Hadamard's acting. What Hadamard's? You can just take the common 0 ket if you just take a common, 1 ket if you just take a common, okay, right? Or a minus 1 ket if you just take a common. What you are going to get is, just now earlier we saw, it is in fact 0 minus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. So when you act a Hadamard on this, what you will get? You will get psi 4 at this point. Okay, sorry, psi 3 at this point is simply 1 ket 1 1, right? So that is what you are getting, psi 3 1 1. Okay, so you just measure the query part and you will give what is the S string. Okay, right? So this is how this circuit works. Now when it comes to implementation, what I suggest you people to do is, either you can take IBM experience, okay, IBM quantum experience, or you can take the Q inverse. Let me show you IBM quantum experience, a composer. There is no need of having an account there. Okay, you can set up the required algorithm. Okay, I hope they still allows you to put up some algorithms. But anyway, I suggest you to use the CDAC or Indian simulator, which is Q inverse, QN inverse.in. Probably the CDAC people are going to show you some simulations. But when it comes to Bernstein's Vajrani algorithm, I'll show you how to implement. Okay, so they have everything ready made. Okay, so let me show you how do you feed is, you create an account. Please, you need to create an account. When you just search qn inverse, this is the account you will see. Okay, and you have to register. Once you start registering with your institute email ID, you register. They will, I think they will activate in a day. From second day onwards you start using. So this is, I'll have now. Here I can create whichever circuit I want. Let's say I want to create an entangled circuit. So let me do two quantum resistors, two classical resistors. Okay, save. So two quantum resistors are there, two classical resistors are there. So first thing is, Hadamard gate acted on the first quantum resistor and control not on the second quantum resistor. So this creates an entanglement. You say 0001, sorry, 11. Entanglement is created. Okay. So that you can see at the bottom in terms of probability. If you want to say in terms of state vector, that also you can choose. The probability amplitude of state vector is 0.707, which is 1 by square root of 2. If you want to have a probability which is 50%, 50%. It's a simulator. It gives you a absolute value. So this is an entanglement circuit for you. Now I am not going to do entanglement. What I am going to do, I am going to do a Bernstein's Vajrani algorithm. Just click on the three horizontal lines. Here on the left you have algorithms. Okay, all the algorithms are there. Beautifully they have done. Okay, right? For a very starting, this is a very good option. Now what do we want to do? We did Dutch algorithm, Dutch Joyce algorithm. For a Dutch algorithm, sorry, Dutch Joyce algorithm, you can fix whether a function is balanced or constant. Okay, and right, so function balanced or constant, and then find out. Okay, right now what we want is Bernstein's Vajrani algorithm. Where is that? Here it is. Okay, the third one. Now, so you want to implement Bernstein's Vajrani algorithm for how many qubits? Is it 2 qubit or so on? Let's say right now we are implementing for 2 qubits. We can go up to 9 or 10 qubits. Right now, let's say 2 qubits. What is the secret key? Secret key is a shift function. Yes. What is the shift function we want? Let's say I want to implement 1 1, the one which we just had in our presentation. So in our presentation, shift function is 1 1. So corresponding to that, I will ask the system to please load the circuit. So it loads the circuit. You see, this is a circuit I have. Circuit even makes a measurement and gives us the output 1 1. So there is a confusion here. Please remember, in the Qiskit or in IBM experience anywhere, the first entry, the topmost entry is the rightmost qubit. The second one comes to the next. The last one comes to the left extreme. So here, the last means the left hand side entry. Okay, let me enlarge. The left hand side entry 1 is correspond to ancilla qubit. The rightmost is Q0, the mid one is Q1, and left one is the Q2. So if you are reading output which is 1 1, so our shift function we found out using this circuit. Now just to see the difference, let's say my shift function is 1 0. Okay, what I want, let's say I want yes being 1 0. Let's say this is what I want. Question is, what is the corresponding circuit? What is the corresponding circuit? You can come up with this circuit by trial and error method. Lucky for us, it is being done already. What do you do? Go back, go to algorithms, and now just enter. Instead of 1 1, you enter 1 0. Okay, enter. Sorry, next. Okay, where is that? 1 0. Load the circuit. It will take some time. Now you see the previous to now, the circuit is slightly different. If you notice earlier, I had control not running from even from Q0 to ancilla qubit. Okay, what happened? This yeah. So the layer is just moving. Yes. Okay. Earlier I had a Q0 to Q2. There is a C0 which is now disappearing. Only I have Q1 to Q1 to Q2. So you can understand, I am just drawing S function from S function is 1 0, right? What did I get output? I'll get 0 1. It is a reverse. Okay, that's how you should read. Okay, so 1 0 is your output. Fine. Now if I want, let's say I want the quantum algorithm with the 0 1. Earlier I had a 1 0, right? Now let's say 0 1. Okay, right, 0 1, load the circuit. So the Hanuman, sorry, C0 gates is slightly, okay. Does it happen? Okay, it's stuck somewhere. Maybe let me refresh. Yeah, see, now the C0 gate is between Q0 to Q2. That is the difference between 0 1. See, now I have a 0 1, right? So the Q2, sorry, a Q2 is on the right. Okay, Q0 and Q1 mid to left. Fine. Okay, so this is how. Let's say you can also go with the 0 0. Let's say my S is just 0 0. Let's understand in a much easier way. 0 0, load the circuit. I'll not have any C naughts at all in this case. See, no C naughts. My output is 0 0, right? And the ancilla is there at the left extreme. Okay, so now we just tried with the 2 qubit. Let's say, as per my PPT, there is one more circuit we want to explore. One more circuit is my S is 1101. 1 1, my shift function is 1101. So here, as per our notion, wherever there is a S is 1, I'll have a C naught running from that qubit string. Okay, so Q naught Q1, Q3, Q2, no control not running. So that is what it should be. Now let's say we will have that algorithm. Okay, algorithm. Okay, so what is the number? Number is 1101. Okay, load the circuit. Okay, I have to change the number of qubits. Number of qubits is 4. Okay, now load the circuit. Yes. See now? It has come up. Okay. What is the output? Output is, okay, just a minute. Output is 1101, right? Sorry, 1101. Okay. Okay, I just made some, yeah, 111101. Okay, so there is, yeah, this one. This correspond to this. Okay, let me, probability amplitude. It is giving for me triple one. Is it a triple one? No. Well, yeah, we need to pick. See, 1, 2, 3, 4, 5, 6, accordingly. So this is the one. 1101. Okay. So let me take all ones. I think that would be easier. Understand? Algorithm. Okay. 4 qubits, all ones. 1111. 4 ones, load the circuit. Okay. Circuit is coming perfectly. And what is the output? Output is all the ones. Okay. Right. So let's take a probability state vector also. All ones. Probability distribution is also all ones. Fine. So this is how you need to implement your circuit. Now what you do, you can write a program depending on the bit string you shift. If somebody introduces, according to that shift, yes, you can modify the required circuit. So what is the circuit program? Here on the right you can find out. Okay, right. So is there a way I can magnify? Yeah, I can magnify. Okay, so I am not able to only get this. Yeah, I can just copy the code. Copy the code. Code is copied. Let me paste it somewhere here. Okay, right. Now do I paste? Control V. Okay, it's not doing. Control V. There. Yeah. So in my code, what it's consisting of, you see carefully. We need to import the quantum register libraries, quantum circuit libraries, backend Qasim simulator. Number of shots is 1025. We need to start the quantum circuit with the 5 quantum registers. You know why? One ancillary register adding. Okay. And classical registers 4 are required because we make a measurement. All 4 qubit registers, square registers will go and use the classical register for the storing the information. Okay. And we'll add the names Q and C, and here we will have Hadamard gates from all the way to Q0 to Q4. Okay, and C0, the controls from 0 to 4, 1 to 4, 2 to 4, 3 to 4, and Hadamards. Okay, Hadamards for 3 and 4. Okay, right, and then make a measurement and send the information, run the shots on the back end and get the results and read the counts. This is the circuit would look like. Okay, right? For this. Fine. So there is one, I think I see Adamarts. Adamarts must be acting on, yeah, here Adamarts are there. After the C naught, there is a Hadamard. After the C naught, Hadamard 1, 2, 3, 4, and yeah, 1, 2, and then 3, 4. Okay, that's fine. So this is the Bernstein's-Vajrani algorithm. So what the Bernstein's-Vajrani algorithm says is, if somebody uses a bit string, which I don't know, right? We will ask them few queries, okay? Whether it's the first bit entry of that bit string is 1 or 0, and next we'll go to the next bit string. So if I had to find 1, 0, 2-bit string, yes, I have to find. So I would be needing two queries. But if I do a circuit, how do I create a circuit? I'll ask the person to entry his bit string without telling me into the program. According to that, the program will create the circuit, quantum circuit, and from that I'll feed my argument x into that. What is the x I am feeding? My x I am feeding is, okay, this one, okay, and that is, this part is designed as per the S, which I am not able to see. Let's say this is the unitary function, let's say Bob is using, okay. What I'll do, I'll create, like Alice will create her quantum state, give it to Bob, okay, Alice prepares, give it to Bob. Bob processes it and gives back this part to Alice. Now Alice what is does? She processes using Hadamard gates, and she makes a measurement. Okay, she makes a measurement and gets what is, okay, what is yes in a single query. Okay, right? You can think that the circuit is with the Bob. We don't have a circuit with us. The Bob has a circuit. Only thing he has to do is he has to process the information, the psi I am giving to him, and return what is the psi output to us, and we will analyze the psi output, or the Alice will analyze, and she figures out what is the yes is, what is the shift function is. Okay, right? So this is the Bernstein-Switch-Dani algorithm, and even I had shown you the implementation. Okay, so you can just check any kind of a uh, bit string, let's say 10 qubit. Okay, 10 qubit, what is the number? The bit shift string, let's say I have 1 2 3 4 5 6 7 8 9 10. This is a bit string. Let me note the circuit. Okay, let's say Bob is using 10-bit string function. Okay, right? So it would look like this. Now if I process it, okay, so I made a mistake of, yeah, yes, I should not. Okay, now you see, okay, I should not mess up. The measurements are getting messed up while moving. Okay, okay, so my probability distribution is, okay, let me recreate again. 10 qubits, 10. Okay, what I'll have 1 1 1 2 3 4 5 6 7 8 9 10. Load the circuit. Okay, so okay, only circuits with fewer than 6 qubits can utilize the probability simulation. Okay, let's say probability vector it can give, even that is the problem. Okay, the system is having an issue. What we can do, go for 6 or fewer. Okay, now let me put the number, bit string, 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, load the circuit. Yeah. Now, yeah, even this one, 6 qubits can utilize fewer than 6. Okay, it is asking for 6 less than 6. Okay, let me go only 5. We just saw 4 and then we will see 5. 1, 1, 0, 1, 1, 1. Okay, load the circuit. At least this should work. It is working. Okay, right? So fine then. So this is the one. You see the right. This is the rightmost line. This is second line. This is the third line. 1, 1, 0, 1. That is what we had. Okay, right. So this is the Bunsen-Swajrani algorithm. In tomorrow's session, what we will do, we'll go for Simon's algorithm. Okay, and if there is any doubts here, I will just see. Okay, there is a question here. Let me see a few questions. Uh, tensor in phi. Okay, where is the tensor in phi? Right. I have, okay, tensor product is involved in various places. Okay, from the circuit, I can show you. Yeah, here. So the tensor product is there. So there is a tensor product at the very initial 0 tensor 0. And psi 1 is H acting on 0 tensor, H acting on psi 0. That is a tensor product. And if there is a tensor in phi, the angle phi, okay, it is not there here. It is just minus 1 to the power of x multiplied by, it's a bit by bit. What I mean is s dot x is s1 x1 plus s2 x2. It's like a dot product between two vectors. Okay, right. Target qubit is 0. By mistake, you mentioned it as a 1. Okay, sorry. Thank you for telling me. Okay, so that is, there are no questions here. Okay, and if there are no questions, you can we can conclude now. So what did we conclude? What did we do today is we used, okay, let me summarize. Okay, we discussed Bernstein's Vajrani algorithm. It is like, let's say Alice is there, Bob is there. Okay, Bob uses a function f of x which takes any argument x, multiplies that argument x with a bit string s. Okay, and s into x, the value would be represented in modulo 2, which would be either 0 or 1. So that is a kind of a function he is using. Now the f of x carries the information of shift s. Okay, so I want to find the shift. So this shift is something like, the shift is something like in real world is like an error in the system, error in the system. It shifts my input strings to something else which I don't want, but I want to find out what is that shift. According to, I can make an error correction. So Bob is like the error creating person in my circuit. Okay, I can't ask bit by bit what is the error you are causing, Bob. In that way I lose the time. So I want to find out what is the shift in one shot. So for that, what Alice will do, she prepares all our queries depending on the size of f of x. If the size of f of x is, let's say it's a 4-bit string or 3-bit string, accordingly x is prepared or x value is prepared. If the f of x is causing 4-bit shift, so x would be having x1, x2, x3, x4. Okay, so Alice will prepare that and send to Bob. Bob feeds that egg, f of x, and he sends the output, whether it's a 0 or 1, back to Alice. Back to Alice, just by knowing what is the psi coming out. Okay, if this is psi 1 going in, this is from here I get psi 2. She analyzes psi 2 by acting 4 Hadamard's on psi 2, getting psi 3, and she analyzes psi 3, analyzes, and finds S is a bit string of S1, S2, S3, S4. Okay, so that is what the errors are, how the errors are happening. The bit flips are happening in my string in which locations, whether it is location in the first string or a second string or a third string or a fourth string. Okay, we will find out that. So to do that, I have to feed I have to feed the information of x to the circuit. Okay, right? So there is no need to even know what is the circuit of oracle function would be inside. I don't want that to be known. Only I feed and I get back the output, and I will analyze the output, and from there I'll find out where is the errors are occurring, where is the shifts are occurring. Okay, that is a Bernstein's Vajrani algorithm. Straight away, that's a error correction. It helps in error correction. How do we do? First of all, we find where the errors are occurring. So S is something like carries the information of errors. So from there, we will find out how to do the correction. Whether it's a bit flip correction. So there's a bit flip error correction we can do. Okay, so that is in a way summary. So the circuit wise, if you want me to tell me, tell you, so there will be oracle function which takes a xcat, it takes ancilla, it gives away xcat, and it gives away ancilla, but xcat gets multiplied by -1 to s into x. Okay, right? By analyzing the output, okay, there is a Hadamard here. How many? N. There is one Hadamard here. Okay, 0 N's. This is 1. And there is Hadamards. Okay, right? So this is analyzing the psi 0, psi 1, psi 2, and psi 3. So this is a Bob's part, and this is Alice part. Okay, Alice part, and the output is sent to Alice. Alice will analyze and find out what is this OF is, what is the S is. S is found by analyzing the psi 3. Okay, right? So, sir, can you just explain how to read the output of qubits from the circuit composer of Q inverse? Yeah, that's a very good question. In Q universe, you mentioned leftmost and rightmost. What is that, sir? Okay, thank you very much. Yeah, there's a confusion always, even for me also it happens. Okay, so when you go back, the best way to do it is, okay, let's start a simple composer, quantum composer. Okay, right. So now Let me remove everything. Let me remove. So I have now both the qubits are in 0 0, right? So now I can't differentiate which is written on the right, which is written on the left. So what I'll do, I'll take a not operation and act on the first qubit. So the first qubit is 1, second qubit is 0. So where is that 1 is written? 1 is written on the right and 0 is written on the left. So the way it is written is, okay, if Q0, Q1 is there, the representation of quantum psi naught is Q1, Q0. Okay, I hope I'm right. Let me check. Yeah, first one is 1, second one is 0. So I have written Q0, Q1. Now let me increase to a larger. Okay, so manage. Let me increase that to, let's say, 4. Save. Okay, 4 qubits. Q0, Q1, Q2, Q3. So the rightmost is 1 0 0 0. Yeah, right? So if here 1 2 3 4 Q0, Q1, Q2, Q3. Let's say I have a X gate here. So if I am starting everything with the zeros, what I'll have 1 0 0 0. So what is the psi naught here? Psi naught here is, okay, I have to start from left to right. Q3, Q2, Q1, Q0, which is 0 0 0 1. I should have the histogram at 0 0 0 1. Okay, let me see. Is it that? 0 0 0 1. Now let's add an ancilla to this. Let's add an ancilla. Manage one more. How do I add? I just remove that, make it 5. Save. So 5 qubits are there. Okay, 5 qubits. Even the fifth one, the ancilla one, is being added where? It is being added at the right extreme. Okay, see, it is added the 1 0 0 0. It should be 1 0 0 0. The Q4 is coming at the right extreme. Okay, so if I make a Q4 is also 0, see here, if you please notice, Q4 is coming at the right extreme. Okay, okay, let me change Q4 becoming also 1. Okay, let me see now what is the output. Output is, now you have to count. The first one is 1 2 3 4 5 6 7 8 9, right? 1 2 3 4 5 6 7 8 9. Okay, so this is, if you're confusing at the bottom, what you can do, just click on that. You will see 1 1 1. Okay, okay, 1 0 0 0 1, right? That is what we want. So don't confuse from the bottom. Bottom is slightly confusing. So what you do is just click on that. You will see the last one is a ancilla. So our notion is, right, our notion is, if I have one more Q4 which is with a X gate, so in this case my psi naught would be 1 0 0 0 1. That is what I have. Okay, 1 0 0 0 1. Fine. So sometimes they change the notations from one simulator to other simulator. What you do, you have to calibrate ourselves by doing this small check. Okay, right? So let's say now implement Bernstein's Vajrani algorithm for 4 qubit 1 1 0 1. load. Okay, this circuit we have seen. Okay, okay, wait a minute. Refresh. Yeah, a circuit we have seen. So what is the output? So from bottom it is difficult to note down. Just click on that. I have 1 1 1 1 1 0 1. Okay, the last one is the query part. Okay, right. So just click on that. You would see 1 1. So the left extreme is the query. The right 4 is the, so left extreme is the ancilla. Right 4 is the query. Okay, so that is what I had. So if my S is 1101, so what is my psi 3 would be? Psi 3 would be, okay, psi 3 would be inclusion of the ancilla. I'll have 1101. So this is the ancilla part, this is a query part. Fine. So yeah, I hope it made clear. So leftmost and rightmost, it is called Little India and something like that. So it's based on Qiskit. So in Qiskit also the same story would apply. Okay, so in IBM Composer, what you see is, let's say I have 4 qubits here, all of them are 0. So let's say the right top one is 1. Okay, so if you click here, they will write top one at the right extreme, Q0, Q1, Q2, Q3. Yeah, this is also the same. Okay, right? They will write Q0, Q1, Q2, Q3. So the topmost comes on the right. The bottom will come on the left. Okay, fine. I hope you understand. Fine. Okay then. Hmm. Any other questions? If there are no questions, okay, so we can wind up for today. So let me tell you, till yesterday, I had added every notes, right? Everything to the drive. So please check it if you want. First is for the algorithm BV. Okay, BV algorithm notes. Right. Okay. Fine then. Uh, very good afternoon to all. Good evening to all. Uh, I hope you people are getting. I request you people to just go through it very slowly. It is slightly tricky compared to Dutch and Dutch algorithm. Like I was explaining, using a comparison between Dutch Joysa to Bernstein's Vajrani. In that way, you can, if you do it, you will really understand. Okay. And when it comes to applications, it is like finding a error causing entity inside the circuit, malfunctioning parts of the circuit. Okay, malfunctioning gates inside the entire setup gates. So the moment I find, then how to do error correction is done through the error correction method. So that is one, and even it is being used in cryptography. I mentioned that here. Okay, here I guess somewhere. Okay, wait a minute. Maybe somewhere I mentioned. Yes, error correction and cryptography. Okay, so 5 minutes till 5 o'clock. I can wait if there is any questions. If not, we can just stop at this point. Okay, and ask the organizers to wind the meeting.
Thank you so much, sir, for the insightful session.
Thank you, sir. Thank you.
So I think there is no more questions, so we can uh, conclude this session for now, and we will continue tomorrow
Yeah.
for the next session.
Yes.
Thank you,
Tomorrow
sir.
would be Simon's algorithm. Yeah.
Sure, sir.
Thank you all for
Okay, sir. Thank
listening.
you so much.
Yes, everyone. I just uploaded the notes to the drive. Canva. You people can check. Okay, everyone. I think there are no questions. Thank you very much. So I'll just log out. You can wait.
Yes, sir. Thank you so much.
Yeah, 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 yeah.